Good afternoon, Warrington. For the last half hour or so, we've been watching cosmic rays, but let's start the talk proper, as it were. Okay. Let me tell you what it is I'm going to be talking about. This talk will give a brief introduction, and before launching headlong into cosmic rays, to make sure we've got a little bit of context, I'll be telling you a little bit about background radiation more generally, a lot of which comes from the Earth. In other words, radioactivity, before we start talking about beyond that. Then I'll briefly talk about the discovery of cosmic rays a little over 100 years ago, the history of that, and then I'll be looking at what sort of detectors exist that allow us to see cosmic rays, or at least detect cosmic rays. And I'll finish with asking, well, where do they actually come from? Saying they arrive at Earth is one thing, but what is the source of these cosmic ray particles, these charged particles that are flying around the universe? And then I will summarize. Before I launch headlong into anything, the U3A lawyers require me to say that on the front table here I have some radioactive samples for demonstration purposes. They are naturally occurring elements. In other words, I bought some little bits of rock that you can dig out of the ground. They just happen to be little bits of rock that contain a little bit of uranium, so they're radioactive. There is no risk to any members of the audience, okay? I'm going to be using them at the front here. You're all at a suitable distance. When the demonstrations are done, I'll put the radioactive samples to one side, and then you're quite welcome to approach the table and have a close look at what's going on here, if you so wish. I've got two detectors on the front bench here. One is a so-called Geiger-Müller detector, or otherwise known as a Geiger counter, and also there's a cloud chamber, which is something I built myself for the purposes of demonstrations such as this particular talk. So let us start by listening to what's going on here. Let me swing the video camera around so you can see. This is the Geiger counter, or the Geiger-Müller tube. And you can see it's not registering zero, even though the radioactive samples are a long way away in a box that's shielded with metal. This is simply picking up background radiation. This background radiation is pretty much everywhere, all over the surface of the Earth. No matter where you go, you'll pick up a few counts per second, a few charged particles going through the detector, a few per second, maybe a couple per second. So we can ask ourselves, let's just get rid of the clicks. We can ask ourselves, what are those clicks? What is it that's doing the clicking? Each click signals the arrival of a subatomic particle, a charged particle of some kind or another, passing through what most people call a Geiger counter. Physicists don't like that because it doesn't acknowledge the fact that it was invented by two people, Geiger and Müller. So physicists call this a Geiger-Müller detector. Everybody else calls it a Geiger counter. And the thing we have to remember is that that's all it does. All it does is effectively count and tell you how many things are passing through. It doesn't tell you what they are. So each click is a subatomic particle passing through the detector. But where did it come from? Well, it might have been spat out from an atom lurking somewhere in this room, producing the click in the Geiger counter. But it's also possible that the click was produced from a source that is much, much, much more distant, perhaps even a supernova that went off a long time ago in a galaxy far, far away. The point is, a Geiger counter can't tell you. A Geiger counter literally just clicks, meaning something has arrived, and it will tell you the rate at which they're arriving. So that's why Geiger counters are useful. You can tell the rate at which radiation is being produced, but you can't tell what it is. If you want to identify the particles, you need something else, and we'll come to that in due course. So let's have a think about background radiation. We have to remind ourselves, radiation is around us all of the time. We've lived with it all of our lives, and it's not necessarily anything to be scared of, at least as long as it's background radiation and nothing too serious. I wouldn't go and stand inside a nuclear reactor. That's a different kettle of fish. Before dealing with cosmic rays, we have to remind ourselves of the radiation that's coming from the Earth itself. We have to remind ourselves that we live on a radioactive planet. The Earth is radioactive. Radiation isn't something that's somewhere and not other places. It is everywhere because we live on a radioactive planet. The Earth was radioactive when it was made, 4.54 billion years ago, and it's still radioactive today. The periodic table, we're not going to go through all the detail, but we've got 100 or so elements that we know about in the periodic table. Some of the elements in the periodic table comprise stable atoms. In other words, once you make that atom lives effectively forever. You might add an electron or take an electron away, but essentially the atom is unchanged forever, for billions of years. But there are some atoms in the periodic table that are unstable. They are not happy being what they are. They want to change into something else. Physicists talk about decaying into something else. Decaying doesn't mean the atom goes moldy. Decaying means the atom changes into another atom. The element changes into another element. And in the process, the nucleus of the atom emits some subatomic particles. And we can visualize that by taking a particular example. What we're going to do is take a particular example, which is this one here. So let me just move forward and click onto the live demo. So we're going to switch to this particular piece of glass is the first thing I want to show you. It's a piece of glass which has deliberately been doped with a little bit of uranium. Why do people put uranium into glass? Well, if we put it in front of the Geiger counter, we can see that this particular piece of glass does indeed elicit, perhaps you can see, I haven't put the speaker back on, but you can see that there's quite a few counts per second coming from this piece of uranium glass. People do not put uranium in glass because they want it to be radioactive. People put uranium in glass, and have been doing for the last century or so, because it gives the glass a different property, and that property is fluorescence. So if you put this in your cabinet and put some UV light on it, you get a rather nice effect of the fluorescence of the glass. So that's the reason uranium goes in. It's nothing to do with the radioactivity. That's just, if you like, a byproduct. And for the purpose of anybody watching the video rather than watching live, what I've just demonstrated is the fact that uranium glass fluoresces rather brightly under ultraviolet light. So that's not suitable for giving a demonstration of seeing radioactivity. We need something else. So I'm going to take a small sample of a little mineral that's called studite. It's one of many samples I've got here, which are tiny. They're only barely a few millimeters in size, but let me just demonstrate that even though it's small, it is actually kicking out something. If I hold it in front of the Geiger counter, sorry, I didn't realize the video wasn't quite centered. Okay, so we've got quite a few counts of something coming out of this tiny piece of rock. Let me switch back to the cloud chamber and actually put it in there and see what we see. I've just disturbed the cloud chamber by opening it up, which means the alcohol in there that was condensing into clouds and then showing us the contrails, much like an aircraft flying through the sky, would produce contrails as the aircraft flies through a part of the atmosphere laden with water at just the right temperature to condense into a contrail. Remember, contrails don't form when aircraft are low. You have to go quite high to get the right temperature. And similarly, you need the right temperature for contrails to form in the cloud chamber. So having just opened it up and disturbed it, it's going to take a minute or two, which is why I am waffling, to try and give it time to actually settle down. And then hopefully, before too long, we will start to see perhaps the cosmic rays that we saw before might come back again in the background, but hopefully it won't be too long. We can again, I think you can now see the drizzle is quite definitely there, raining down onto the plate at the bottom. The cloud chamber is warm at the top and cold at the bottom. It's like an atmosphere, but upside down, which is generally warm at the bottom and cold at the top. And hopefully, before too long, we will start to see some activity. Let me just kill the Geiger counter so we're not continually clicking away. Again, if anybody would like to shout as soon as they see something. Did you see that one? Yep, okay. Just look out for any lines that appear to be radiating from the rock. Yep. given that it's quite pretty, let's just wait a minute or two and let them build up a bit. Now that the cloud chamber is settling back down, these contrails should be easier to see. And although it's only a tiny piece of rock, remember the plate we're looking at is only a few centimeters in size, so the rock is only a few millimeters in size. It's got quite a few uranium atoms in it, and those uranium atoms are spitting out something. We can quite definitely say, simply by observing, just by eyeballing, we can say that rock is spitting out something. Every once in a while you might see a track that does not start or finish at the rock, in which case that's just another cosmic. But you can see that the number of tracks coming out of that rock is far higher. This is far more active in terms of the number of particles per second than the cosmic rays we were looking at just a moment ago. So you can see that it's in fifth gear now. It's really spitting out all sorts of things. It's always been spitting out that number. It's only a question of visualizing them in the cloud chamber when the cloud chamber is good and ready. Perhaps you notice, it may not be absolutely obvious with this sample, but it may be obvious that we've got some tracks which are very narrow and relatively bright, and some tracks which are relatively broad and fuzzy and not quite so clear, slightly more ghostly. Yeah, do you see those? Every once in a while you get something coming off, and then you get something that's virtually 1 pixel wide in this particular image. So there's something coming out of that rock, and there appear to be 2 types of something coming out of that rock. Okay, let's go back and ask ourselves what's going on. This is a different rock, and in good Blue Peter fashion, I videoed this before coming out today, such that if the live demonstration didn't work, I still have something to show you. So this is a different piece of rock. This piece of rock is called Boltwoodite, but it's similar in the sense it's got some uranium in it. And again, you can see different tracks coming out. Occasionally they look a little bit, this one is not quite so active as the other one, so we're not getting quite so many tracks. Every once in a while a rather fuzzy track comes out, and every once in a while a very distinct narrow track comes out. I took videos of this, and I took a video for a minute or two, and then I went through the video and I picked out the frames that seemed to have nice tracks on them and put those together into a composite image. So that, if you like, is a sort of a time lapse of 1 minute's worth of video. And again, it's a little easier now to see that some of these tracks are relatively narrow and are barely 1 pixel wide, and some of them are relatively diffuse and rather more ghostly and rather broader tracks. So we might guess that there are 2 types of particle coming out of this rock. So it's emitting something quite definitively. So what do we think they are, and where do they come from? Let's remind ourselves what atoms are made of. Atoms have got a positively charged nucleus comprising protons and neutrons. It's actually only the protons that are charged, but that doesn't matter so much for the moment. And we have a whole load of electrons buzzing around the outside. But when it comes to radioactivity, and whether or not an atom is stable or whether an atom is unstable, is nothing to do with the electrons that are buzzing around on the outside. Radioactivity is determined solely by the nucleus. That's the only thing in an atom that makes a difference to radiation and radioactivity. So even if we at some point talk about electrons flying around, it's not these electrons we're talking about. It's not the electrons that make up the atom. It's what's going on in the nucleus. And the nucleus, if it's unhappy being what it is, remember, if it's stable, if it's happy being what it is, then it will live forever. But there are some nuclei of atoms that are unhappy and want to change into something else. Let's imagine we had a really heavy nucleus, a bag full of shed loads of protons and neutrons. That might want to change into something else, and it could do it via a number of different means. Different nuclei will behave differently, but hypothetically, what could a nucleus do? It could decide that it's got far too many protons and it spits one out because it's happier with one less proton. We're not going to worry about the whys and wherefores. That's physics. That's nuclear physics. But it might be that a nucleus wants to get rid of a proton. It might be it's got far too many neutrons for its liking and it wants to spit out a neutron. It might be that it's got far too many protons and neutrons and it spits out a couple at a time. A particle called an alpha particle, which comprises 2 protons and 2 neutrons. That particular collection of objects is also called the nucleus of a helium atom, because that's precisely what helium is: 2 protons, 2 neutrons in the nucleus of an atom. So an alpha particle, it was called an alpha particle, we now know it's the same thing as the nucleus of a helium atom. A nucleus might decide to chuck out an electron. On the left, if it chucks out an electron that's negatively charged, that's the electron that we know and love. That's the one that's buzzing through our electricity circuits and our electronics and our laptops and our phones. That's the familiar electron. But it might also spit out a different type of an electron, one with a positive charge, the opposite charge to an electron. So electrons are what we call matter, but if it has the opposite charge, it's what we would label antimatter. It looks like an electron, it's got the same mass as an electron, it's got the same amount of charge, but it's the opposite sign. It's plus rather than minus. So that's what we would call an anti-electron. Every particle has an antiparticle. Nuclei can spit out antimatter equivalent of electrons. And finally, it is also possible that the nucleus isn't happy being what it is, and it wants to spit out an electromagnetic wave, a gamma ray, to lose energy. It's not, strictly speaking, a particle in the same sense that these other ones are particles, but it can behave like a particle. It's a photon of electromagnetic radiation, a gamma ray. We're not going to discuss or think about all of these things. We're just going to think about the three most common types of radiation that get encountered and often mentioned at school, for instance. The three most common types of radiation are called alpha, beta, and gamma. And we've met we've met all of them already. Alpha rays, or alpha particles, the difference between a ray and a particle is just history. When they were first seen, people didn't know whether they were rays like light rays or whether they were particles like solid objects or objects that they could recognize as a particle. So they were called rays. Some people now call them particles. It really doesn't matter. Alpha rays, alpha particles, they are the same thing. They are comprising 2 protons and 2 neutrons, and they're otherwise known as the nuclei of helium atoms, and they're quite heavy. So they don't travel very far. In other words, they don't travel very far through air, and they can't get through the glass of the cloud chamber. So any alphas that we see in the cloud chamber must have been there in the first place. In other words, the atom that spat them out must be inside the cloud chamber because they can't have got through the glass. Beta rays, or beta particles, are essentially electrons, possibly their antimatter equivalent of electrons, and electrons are much lighter than protons and neutrons, and so they can penetrate further, and in a cloud chamber, because they're so light, they ricochet off everything that's in there, and you get a very wiggly path when you look at them in a cloud chamber. Gamma rays was the third one that tends to get mentioned, but we're not going to see those in a cloud chamber because they do not leave a track. They do not leave a contrail as they pass through a cloud chamber. So having established that that's what they are, let's switch back to the sample, which is still radiating away. Even though we turn our back on it, it still radiates just as fast. And now we can start to recognize that the broad ghostly tracks, they're the ones from alpha particles. They are the bulldozers of the particle world. They're very heavy, they're quite energetic, and they will produce very broad tracks. They will produce a lot of droplets as they go through the cloud chamber. Whereas the narrow ones tend to be electrons, much lighter, and they can be, depending on their energy, rather more wiggly. So now we can start to recognize what it is that's going on inside this cloud chamber. And because we are effectively done with this radioactive sample, and I don't want to leave it in there, I'm going to remove it such that we can do other things later. So let me just see if I can do that without disturbing the cloud chamber too much. Whoops. It's going to take a while for the cloud chamber to recover, but that's okay. Meantime, we're going to go back to the PowerPoint. So again, Blue Peter fashion. The one I was looking at earlier, we see quite distinct narrow tracks. So the narrow tracks are the beta particles, or sometimes I just call them electrons because it's not likely we're going to get that many anti-electrons in the system. And the rather fainter ghostly tracks are the alpha particles, the rather broad ones that bulldoze their way through the cloud chamber and produce broad tracks. So we can definitely see this type of radiation, and again, that's the composite image, just to put the narrow betas and the broad alphas side by side. What can sometimes complicate the issue is the fact that because we are talking about a cloud chamber and alcohol is raining down and condensing into droplets, which gives us the contrails that we're seeing, we are eventually building up alcohol in the bottom. So it is pooling, it's coming down from the top. I put the alcohol in the top. Slowly, the alcohol is pooling in the bottom, and eventually you'll start to see reflections because you're effectively looking in a swimming pool of alcohol. So some of these tracks look a bit odd only because you're seeing the reflections of the tracks as well. Bear that in mind if you come and have a closer look later. So another couple of things we need to know just to make sense of what we're talking about later, and that is isotopes of atoms are effectively cousins of the same type of atom. As an example, let's just take an atom you're familiar with, carbon. There's a huge amount of carbon in your body. Carbon has 6 protons in the nucleus by definition. If an atom has 6 protons in the nucleus, that's what we call carbon. Carbon is simply the label we use for an atom whose nucleus has got 6 protons. And the number of neutrons is up for grabs. For instance, a carbon atom might have 6 neutrons in the nucleus, in which case it's got 6 protons, 6 neutrons, 12 in total. We call that so-called isotope carbon-12. It's a particular type of carbon. Most of the carbon in your body is carbon-12. But carbon comes in other varieties. You can actually squeeze 8 neutrons into the nucleus, and there's another couple of blue ones you might notice compared to those over there. There's another couple of blue ones in there. So we've now got 8 neutrons. Same 6 protons, but now 8 neutrons. We call this particular isotope carbon-14. Carbon-12 is stable, just as well, because that's what you're made of. Carbon-14 is radioactive. You've heard of carbon dating. That is what is used in carbon dating. How much carbon-14 is in this thing that I'm trying to measure to try and figure out when it died. Carbon-14 gets absorbed by all living things in very small quantities. And because it's radioactive, you can work out how much there is in a sample and use that to date the sample. So having a radioactive isotope of carbon is very useful for us to work out how old things are. How many radioactive elements should we think about? There might be a few more than you think. One of them, perhaps surprisingly, is potassium. Everybody's heard of uranium, but potassium is the most abundant of the radioactive elements in the Earth's crust. If you work out how much potassium is in your body and how many of those atoms are radioactive, it's been calculated that something like 4,000 potassium atoms decay or change every second. So you are radioactive. You are emitting radiation. You are spreading radiation to your neighbors as we speak. So again, when you think about radioactivity, you tend to think about something over there that's radioactive. You don't think about the fact that you are radioactive as well as the person sitting next to you. Potassium is one of the largest contributions to natural radiation. Thorium is a radioactive element which is actually more abundant than uranium, which everybody has heard of, and even uranium is probably much more abundant than you think in terms of how much is there in the Earth's crust. It might not sound much, 3 parts per million, but actually that's way more than the amount of gold, for instance, in the Earth's crust. It just happens to be more difficult to get out of the Earth's crust, which is why you don't have much uranium lying around, but bank vaults are full of gold. So uranium, it is possible to dig it up, and it is radioactive, and of course it has its uses. But bear in mind that potassium and thorium and uranium exist in the Earth's core in fairly large quantities. And it's the decay of those radioactive elements that release energy and hence release heat. They have been keeping the core of the Earth molten for the last 4.5 billion years. The Earth is warm not because of the radiation from the sun. That heats the surface, but it doesn't heat the core of the Earth. The core of the Earth has a molten core because of the radioactive elements that have been decaying for billions of years. So rather ironically, radiation is keeping the core molten. A molten core that rotates generates a magnetic field, and hey, the magnetic field helps protect us from radiation from space. It's a beautiful circle of life in that sense. Whilst I'm talking about potassium, there is one isotope, one cousin, remember, with a different number of neutrons in the core. There are what's the percentage? 0.01%, a tiny percentage of potassium is potassium-40. That's an isotope which actually spits out beta plus radiation. As I mentioned before, beta means something that looks like an electron, but beta plus means it's got a positive charge, not an electron's negative charge. So potassium kicks out antimatter. That means anything that's rich in potassium is an antimatter producer. So, for instance, that is a radioactive sample. Because bananas are rich in potassium, it's not going to set off the Geiger counter. It's not that much coming out of it, but we know there is potassium in bananas, quite a lot of it, and Brazil nuts and other certain foods. And we know that a certain fraction of potassium emits antimatter. So this banana is emitting antimatter. Not much, not enough to get the front row concerned, but it is doing that. And because bananas are radioactive, just to give a sort of sense of scale, somebody came up with the banana equivalent dose. Rather than talking about how many sieverts or rads or rems or becquerels or all these weird units that physicists come up with, can't we talk about radiation in terms of how many bananas? Isn't that an easier thing to get your head around, especially at the very low level of radiation? Might not be very useful for a radiation worker going to spend time in a nuclear reactor, but in terms of everyday doses, it's actually a sort of useful dose. I'm not going to spend too much on that, but just to put it in perspective, if eating one banana gives you a certain dose, that's the banana equivalent dose, we can ask the question, at the moment, cosmic rays are coming through the roof and through the walls and going through you. What is the dose of cosmic rays that everybody gets every day of their lives? How much is that compared to the amount of radiation that you would receive because of the potassium that's in a banana? Well, the dose of cosmic rays per day is approximately equivalent to a dozen or so bananas. Bear in mind that if you spend a lot of time flying, you're above part of the protection of the atmosphere, you're closer to the cosmos in a sense, and so you'd have to think about doubling that. That's why airline pilots have to be careful about how many hours they do, because they pick up a larger radiation dose because of the time they spend at altitude. Let me finish this section just with one more comment, and that is, as well as radiation from rocks that you can dig out of the ground, there is another source of radiation, which is a gas. Not all radioactive samples are solids. There's one notable one that's a gas, radon. Radon is a radioactive gas which is formed by the decay of small amounts of uranium. When uranium changes, it changes into lots of different things, including radium and radon. And whenever you have uranium in the ground, and we don't think of the ground under our feet being particularly doped with uranium, but there is a fair amount in there. When we look across the UK, we find there are certain hotspots of where radon occurs because that's where there is more uranium. Why is there more uranium in these particular places indicated in red? Because uranium quite often occurs in granite. Only small quantities, but that's all we're talking about. So whenever you have granite, like the Highlands or the Pennines or Cambria or Devon and Cornwall, wherever you have a lot of granite in the ground, you will have more than average uranium. And that uranium will decay into radon. Radon is a gas, and it won't stay in the ground. It'll bubble out and it'll come into the air. And radon gas emits alpha particles. So we can see that we in Warrington, where are we? Somewhere around there. So we're in a relatively, it's sort of pale blue. That's not necessarily zero, but it's a very low level. So there is not much radon in this room, simply because we don't live in an area with a large amount of granite under our feet. And by not much, it might sound a lot, but the number of atoms of radon in this room might be about, about 1 billion or so. And if that sounds scarily large, remember that is tiny compared to the number of atoms of oxygen and nitrogen, which is 1 million times more or thereabouts. So there is radon in this room, and we might see it in the cloud chamber, but it's tiny, tiny levels. It would be higher, and we'd get more activity in the cloud chamber if we took the cloud chamber down to Cornwall or Devon. I have no plans to do that just yet. So that gives you a little bit of context. So having got an idea of what we mean by radiation radioactivity and what's going on the Earth, we can now ask ourselves what's going on from above. So at the end of the 1800s, in the early 1900s, people were experimenting with this newfound thing of radioactivity. I would imagine you all know the person in the middle, Marie Curie. You may not have heard of Becquerel or Hess. Becquerel discovered radioactivity. He looked at photographic plates and said, why are these photographic plates getting fogged, even though they're in darkness, when I put them close to uranium rock that I happen to have as a paperweight? If I put the uranium rock in the same drawer as the photographic paper, even though the photographic paper never sees the light, they still get fogged. He discovered radioactivity. Marie Curie then purified various elements that were derived from uranium, like radium and polonium, etc. And Hess was effectively the discoverer of cosmic rays, which we'll see in just a moment. So where did this idea of cosmic rays come from? Well, people at the time were using gold leaf electroscopes. These are ways of determining charge. It's basically a jar to avoid any air currents and a little bit of gold leaf in two strips. If you charge it up with positive or negative charge, remember opposites attract and like charges repel. So if you were to charge that up, the two pieces of gold would have the same charge. They want to repel each other, and so they will literally just separate, just because they want to separate. If you charge that up, what you observe is, over a little bit of time, they will slowly discharge and come back together again. It's as if you're adding some positive or negative charge into the system. Why do these things discharge? So when these were being used at the end of the 1800s, in the early 1900s, the fact that these so-called electroscopes discharge told people there must be some charged particles flying through our electroscope. Where are they coming from? Are they coming from below our feet, or are they coming from the sky? Didn't know. So a physicist said, okay, Theodore Wolff, a physicist, said in 1910, I'll take an electroscope, I'll measure the amount of radiation down here by how quickly the electroscope discharges. I'll measure it down here, then I'll go to the top of the Eiffel Tower. If the radiation readings go down, then it's coming from the ground. If the radiation readings go up, it's coming from the sky. Great logic. Unfortunately, it didn't work because they realized that the radiation levels were changing, but not by the amount that you would expect. If they're all coming from the ground, you would expect it to go down even more than they observed. So something is complicating the matter. It's not just the ground or just the sky. What's going on? Well, is it possible the Eiffel Tower is radioactive? No, that's not a silly statement. The Eiffel Tower is made of iron. Iron is dug out of the ground. The ground is radioactive, or bits of it are. So is it possible the tower itself is radioactive? And at this point, radon was known about. So is it possible there's a lot of radon in the air, and so going up the Eiffel Tower really doesn't tell you anything? This is where Hess came in and said, going up the Eiffel Tower, that's not enough in terms of a height difference to be able to tell the difference between is it coming from the ground or is it coming from the sky. To resolve that, Hess said, we need something different. We need more height. Okay, Eiffel Tower is about as high as you can go, so what's the alternative? He decided to make electroscopes that could be taken up in a hot air balloon. Then you're not limited to the height of a tower. You can go almost as high as you like. So in 1911, 1912, he took some electroscopes in his basket. That's him in the middle there with the hat. He took them up and did a number of experiments to try and determine what's going on. What he found was, in 1911, he went to about 1,000 feet, didn't really see much change, which explains why you don't see much change at the top of Eiffel Tower. Even at 1,000 feet, 1,000 meters, you don't see much in the way of change. But then the next year he went up to 5,000 and wham, he suddenly realized the radiation levels went through the roof. So once you'd got high enough, it was obvious that the radiation was coming from above. Doesn't rule out a little bit from the ground, but essentially what's discharging the electroscopes is coming from above. Was it due to radiation from the sun? Okay, how would you tell if it's coming from the sun or not? Well, you go up in a balloon and you say it's higher up there than it is down here. If you want to know whether it's the sun or not, one option is to do your experiments at night. Who wants to get into a hot air balloon and go up 5,000 meters if you cannot see what you're doing and you do not know where you're going to land? Because, of course, that's at the fate of the gods and the winds. Nobody wanted to do this experiment at night, but he wanted to know, how am I going to tell if it's coming from the sun or not? He had the genius idea: you do a balloon flight on a day when there's a solar eclipse. And you go up and you measure the radiation, and when the moon covers the sun, you assume that whatever's coming from the sun is going to be blocked by the moon. Does the radiation go down or not? And the answer was basically not. It does not appear to be coming from the sun. Again, maybe a little bit, but basically most of this is not coming from the sun. This is coming from the cosmos. And that is why Hess was effectively the discoverer of cosmic rays. In 1936, he was awarded the Nobel Prize for the discovery of cosmic radiation. The term cosmic rays and cosmic radiation was coined a few years before he got the Nobel Prize, but he has been credited with the guy that figured this out from these balloon flights in the early 1900s. So we now know that particles are raining down on the Earth. This is a little bit of a fanciful artist's impression. Ignore the Star of Bethlehem right at the top there. That doesn't mean anything in particular. If a particle hits the atmosphere, it produces a shower. That particle does not make it to ground level. A particle that comes in and hits the top of the Earth's atmosphere hits a oxygen or a nitrogen atom or something else, and basically produces a shower of particles, which then produce another shower and another shower. There's a complete avalanche of secondary particles. So we talk about primary particles hitting the top of the atmosphere and then secondary particles being generated in this air shower. We seem to have two air showers simultaneously. Again, that's a little bit misleading. You might only expect one at a time. But bear in mind, one incoming particle can produce thousands of particles that might reach ground level. So this cartoon on the right doesn't show you any of the complexity of what we're talking about. It isn't one particle comes in and half a dozen reach the ground. It's much more likely to be hundreds or thousands or possibly even millions of particles that reach the ground. Primary ones are the ones that hit the atmosphere. Secondaries are the one that we measure, for instance, in a cloud chamber at sea level. At each level of the cascade, at each level of this shower, the particles being created share the energy of what's coming in. So if you know the energy of everything that hits the ground, you can work out how energetic that first particle must have been. The more energy comes in, the more energy and probably the more particles you get reaching ground level. The cascade from one primary might conceivably, if it's energetic enough, produce millions of secondary particles at sea level. What are these secondary particles? Well, they could be a number of different things. Some of them are familiar particles, like electrons. Remember, they haven't come from the electrons buzzing around an atom. They've been generated by an energetic particle hitting the atmosphere. There might be some electrons in there. There might be some protons in there. But some of them are actually, some of these new particles are actually unstable. They are not particles that exist in our atoms. They are not protons or neutrons or electrons. Some of these particles that are made might only live for a tiny fraction of a second. They're made when something slams into the atmosphere, and they effectively die by the time they've gone through our detector and bury themselves into the Earth. One such particle is called a muon. A muon has no part to play whatsoever in atoms, which is why you might not have heard of them, because you might have heard of nuclei and electrons, but not muons. A muon is similar to an electron in its properties. It's negatively charged, but much more massive. It's about 200 times more massive than an electron. And again, it can be very penetrating. It can go plowing through a cloud chamber, quite often in a straight line. A muon, we know from particle physics experiments, does not live very long. A muon might only live for a few microseconds. So if you do see one in a cloud chamber, you know it was born only a few microseconds ago at most, and will probably not live for more than a microsecond or so after it's passed through the cloud chamber. Very much a fleeting glimpse. And that's what a muon might look like. That's a picture I took before. I've changed the contrast slightly so it looks a little bit blacker in the background compared to what we were seeing earlier, but that's typical. A row of dots that is straight and relatively narrow is characteristic of a muon passing through the cloud chamber. We've been talking about the secondaries, what we see when they get down to sea level. What about the primaries? Secondaries might be muons, electrons, protons. We now know what the primary particles are, the ones that are somehow floating around the universe or zooming across the universe and slamming into our atmosphere. We now know from decades of research that most of them are protons. 90% of them are protons. In other words, they are nuclei of helium atoms. If you like, hydrogen that's had the electrons removed, and what you're left with is a proton. 9% of them are alpha particles, otherwise known as the nuclei of helium atoms. Again, take a helium atom, strip the electrons off, what you're left with is an alpha particle, 2 protons, 2 neutrons. And a rather small fraction, because of course we've already accounted for 99% of them, a small fraction would be heavier stuff again. 1% would be heavier nuclei than hydrogen and helium. Which particular atoms? Well, pretty much all of them as far as we can tell. In other words, all of the atoms that we see in the solar system, lithium, beryllium, boron, nitrogen, carbon, oxygen, all the way up to virtually as heavy as you like, all of those seem to be present in cosmic rays in smaller and smaller and smaller numbers. Most of them are protons, a lot of them are alphas, a very small fraction of them are really heavy nuclei. So how do we detect these cosmic rays? Well, we've seen one example, and that is this Geiger counter, which should be called a Geiger-Müller tube. So the Geiger-Müller tube itself is this tube in the front there. The yellow box is basically just a box of electronics that provides it with a high voltage and makes the clicks. So in other words, the Geiger-Müller detector is a cylinder with some gas inside. It's usually an inert gas, helium, argon, neon, something like that. And if you have some incoming radiation, it could ionize one of those atoms, separate the electron from the positively charged nucleus. And if you have a large voltage provided by the yellow box, then the plus and the minus charges will get attracted to those electrodes and will produce a current. So the ionization will then produce a current, and the yellow box just converts that current into a click. There's no other information you get other than something has passed through the detector. So that's how a Geiger-Müller tube works. What about a cloud chamber? Well, a cloud chamber came into existence at about the same time in the early 1900s because one enterprising fellow went up to Ben Nevis and saw a Brockenspector. Has anybody ever seen a Brockenspector? Oh, right, okay. Basically, if you go to the top of a mountain and look opposite to the sun, so you're looking at the shadow of your head, you can get some interesting atmospheric effects if it's very misty, if there's a lot of moisture around. Charles Wilson was interested in this. He saw a Brockenspector in 1894, and he said, I'd like to study that, but I can't study it on the top of a mountain. I need to be able to make a cloud in my laboratory. So he tried to make a device, an instrument, that would allow him to make clouds so that he could study things like the Brockenspector. So he built himself a cloud chamber. In 1911, he basically got it right. It looks a bit odd, but it's a chamber in which you can let gas from a chamber into a larger volume, and so it suddenly expands and then will produce droplets of water. But it wasn't too long after he built this and started experimenting to see what he could find in terms of interesting atmospheric effects. He realized that when he looked in his cloud chamber, every once in a while he saw tracks going through, which he realized were charged particles. Whenever a charged particle went through his cloud chamber, he realized it left a track, a contrail. Water droplets condensed to form visible tracks. So in other words, he could see, especially when he brought a radioactive sample up to it, he could see those positively charged particles or negatively charged particles going through his cloud chamber, leaving tracks behind. The particle physicists immediately jumped on this and said, rather than talk about the possibility of fundamental particles, which we're going to give weird names, we can now actually see them. Thanks to the cloud chamber, we can now actually follow them. We can do experiments. We can bang things together and see which particular particles come out. we can apply magnetic fields and see if the track bends to the left or bends to the right, which tells us whether or not we've got a negatively charged particle or a positively charged particle. So particle physics came on leaps and bounds once this particular device was realized that as well as being good for looking at Brocken specters, it's actually fantastic for doing particle physics. In 1927, he was awarded the Nobel Prize for, quote, the most original and wonderful instrument in scientific history. What a wonderful quote that is. That's how much of an impact the cloud chamber had to our understanding at the beginning of the last century. So his cloud chamber has changed a little bit over the years. Thanks for that announcement, yes. So the 1911 version of the cloud chamber has changed a little bit, and I've built one with sort of a distant cousin of Wilson's cloud chamber. It's, as it happens, about the same size, but I'm not going to talk about the details of its design and construction. I figured that might be a short talk another day. I do have some handouts as to how you can build one for yourself if you're interested. And this particular beastie stands about 20 centimeters high. It's about 10 centimeters in diameter. And the idea of the cloud chamber is you put alcohol in the top and you warm it up to evaporate the alcohol. You cool down the bottom, so you have some cooling here. A little refrigeration kit cools it to minus 25 Celsius. So alcohol evaporates at the top. It then condenses shortly before hitting this cold plate at the bottom. So just above the cold plate, which we can see here as the black rectangle, hopefully that's at the point at which anything that wants to trigger the formation of droplets, such as a passing particle going through the cloud chamber, will just trigger the condensation and produce a trail of droplets, which we then see as a track. So if we switch back to the live video, I've taken the radioactive sample out, so hopefully we're back to cosmics again. There seem to be a few dust specks sitting on there, just making life a little bit awkward, but it gives you something to focus on, I suppose. So we are now talking about the alcohol being generated way off screen at the top. This is a plate. It's a metal plate, which is at minus 25, so it is condensing the alcohol back into a liquid, and just before it hits the plate, is just about the right height, just a few millimeters above the plate. That's the point at which a passing particle might convince it to produce a trail. Anything that happens to be going vertically through will just give you a speck. Anything that's going horizontally through, hopefully, will give you a nice track. So this is pretty much how Wilson must have felt back in 1911. He built this for the purpose of making clouds, but along the way he thought, why am I continuously, every few seconds, seeing lots of things coming through, and then take a radioactive sample, realize that lots of these things are coming through because we're looking at the tracks of particles. Don't seem to have that many coming through just at the moment. Is it worth waiting for one classic corker to come through? It's at this point you could wait 10 minutes and nothing much happens, and then like buses, 6 come along at once. Oh, that's a good point to move on. That was a really nice electron coming through. It was very wiggly, very distorted. Occasionally you see electrons that come along and almost turn round and go backwards because they are so lightweight. That was a nice one as well. They're so lightweight they can easily be scattered by whatever else is in the cloud chamber. So again, here's a video I made when it was in my kitchen, just to prove that it can see. I think every once in a while you get a nice streak coming through. Hey, that was actually a proton. That was a very straight, very bright one coming through, and lots of other little wiggles all over the place. And again, just as before, what I did was take not a minute's worth, because cosmic rays don't come through that often, so I took an hour's worth. I put the phone next to the cloud chamber, recorded an hour's worth of video, and then rather than watch the TV, I sat and watched this thing and made a note of where all the very nice tracks were, and I pulled all of those frames out and made a composite image. So that's what you would see if you had the patience to sit and watch it for the best part of an hour. Most of these in the background are wiggly electron tracks. Occasionally there are straight muon tracks. The really bright ones are protons. I have not put in the alphas because, remember, alphas are not cosmic rays, so they will be seen during an hour. I saw maybe half a dozen of them, But here I'm trying to say these are cosmic rays and alphas are not cosmic rays. So over the course of an hour, you might see hundreds, many hundreds of these tracks, some of which are very small and barely more than individual points. Most of them are, rather satisfyingly, quite long tracks. But because they all have different character in terms of how straight, how wiggly, how wide, you get an idea of being able to tell what these tracks actually are. So we know from history that you can build yourself in principle a cloud chamber. Geiger-Müller tubes are a little more difficult to build, but you know, they were built a century or so ago. But there are other cosmic ray experiments that have been done over the decades. For instance, the Voyager probes flew with cosmic ray detectors on them. That's that little red thing right at the top there. The idea was not to assume necessarily that there will be lots of charged particles coming out of Jupiter or Saturn or whatever, but they will have magnetic fields, it will affect the cosmic rays, and also it meant that as they flew out of the solar system, they could see a change in the cosmic rays as they left the solar system. Back in 2012, Voyager 1 noted a significant increase in the high energy end of the cosmic rays, which were coming definitely from outside the solar system, not from the sun. The sun might be producing some of the low energy stuff, but not the high energy stuff. So we think that Voyager 1 left the solar system in 2012. Remember, it was launched in 1977. Voyager 2 launched at the same time, but it's traveling more slowly. Voyager 2 is the one that went to Jupiter, Saturn, and then on to Uranus and Neptune afterwards. Traveling a little bit slower, it took Voyager 2 longer to come to the same conclusion that it had left the cosmic rays, left the solar system because of the increase in cosmic rays. That happened in about 2018 or so. If we look at low energy particles coming through the detector of Voyager, in 2018 it suddenly took a nosedive, whereas the high energy, what we assume to be cosmic rays coming from outside the solar system, started to increase and then did a little jump. So it was taken as that is the point where we will define that Voyager left the solar system. A drop in the low energy from the sun and an increase in the high energy from the rest of the galaxy. There are also experiments, for instance, on the International Space Station. In the corner here, labeled AMS, that is a cosmic ray experiment. We can have a different view of it. You can get an idea of its size by looking at the astronaut in the top left there. It's a relatively large instrument, and it's monitoring, if you like, what is actually coming down. Of course, the ISS is essentially above the atmosphere, so it's monitoring what particles are coming in before they hit the atmosphere. But as well as that, we would like to monitor what's going on at ground level. So we've got space-based experiments telling us what's up there. It's also possible to have ground-based experiments. This, again, is an artist's impression. Lots of detectors on the ground, and if we can work out what's going on the ground, we can extrapolate and we can work out what must have hit the atmosphere in order to give this many secondary particles hitting the ground. This particular one is the Pierre Auger Observatory in Argentina. It's one of the largest cosmic ray experiments. If you want to catch the entire shower, and the shower might start tens of kilometers up, maybe 30 or 40 kilometers up, the shower itself will have a very big footprint. So you don't want a very small detector that's going to miss most of the particles coming down in the shower. So they figured that what we want is the largest footprint we can get away with. So we have detectors spread over a very large area in Argentina. You can't tell from that map what the area is, but roughly speaking, the area, the footprint of this particular detector in total is about the area of Luxembourg. Okay, it's a bit bigger than that cloud chamber, which is only a few square centimeters. So it's many, many square kilometers in size. So we've got lots of these detectors spread over a very large area. What are these detectors? Well, the detectors are basically tubs of water, and we're looking for cosmic rays traveling through the water. Why are we doing it that way? Well, there's a particular physics phenomena that allows us to see particles that travel through a medium faster than the speed of light can travel through the medium. So remember, nothing can go faster than light in a vacuum. But when we're traveling through water, light is slowed down, and it's possible that very energetic particles will be traveling faster than light can travel through water. What happens when objects move faster than light can travel? Well, it's analogous to what happens when objects travel faster than sound can travel. When you've got an object traveling through the air, if it's traveling faster than the air can move, in other words, it's traveling faster than the speed of sound, you get what? You get shock waves, you get a sonic boom. So a sonic boom occurs when an object moves through air faster than the air itself can move, can get out of the way, if you like. And there's an analogy with light. If you have a particle moving through a medium, whether it be water or air, then it is possible to produce the photonic equivalent of the sonic boom. And so a little animation from one of these telescopes shows what's going to happen when a particle comes in and hits the top of the atmosphere, an instant cosmic ray particle. A photonic boom. Cherenkov light or Cherenkov radiation, a blue glow or a blue flash. But this is a slowed down version of it because it is a flash that's over in a billionth of a second. So if you have telescopes in the Atacama Desert and in La Palma, the southern hemisphere and the northern hemisphere, and you look at the sky, you might be able to catch particles that are moving through the air faster than light can travel through the air. And you can see this blue glow. So the plan is to build lots of these telescopes, a whole batch in the Atacama Desert and another batch on the Canary Islands in La Palma. Different sized telescopes because they'll be looking for different brightness of flashes in the sky. So that's the principle of what happens in the Pierre Auger when it's traveling through water. You get the same flash, you look for the flash. Here, they're looking for the flash in the atmosphere, but there's another way you can do it, another type of observatory, and that's one sitting at the South Pole. There's the Ice Cube Observatory sitting on top of the ice cap. There's the bedrock of Antarctica. There's the top of the ice cap. But we're not looking for things coming through the observatory. What they've done is to drill down into the ice and instrument it with thousands upon thousands of photodetectors, like strings of pearls running through this big block of ice. The block of ice that they have instrumented is approximately 1 kilometer by 1 kilometer by 1 kilometer. It's the largest ice cube in existence, probably. It's 1 cubic kilometer of ice. If you're having trouble with that, there's the Empire State Building on the left-hand side to give you the scale. So you have thousands of these detectors, and you wait for a particle to come screaming through the ice faster than light can travel through the ice. And when that happens, each of your photodetectors might or might not pick up the blue flash as the particle comes through. And by seeing which particular photodetectors see the flash, you can work out, well, which direction in the sky did it actually come from then? And if you know the time and you know your position, you can work out which bit of the sky actually this came from. So you have a chance of working out the source of this particular particle. Right, so the final section is, we've had an idea of seeing them at ground level, we've got an idea of how we detect them, but where are they coming from in the first place? What is the source of these cosmic rays? And some of them are very energetic. Where do they get their energy from? Just as an aside, let's remind ourselves that it's 2024, and back in 1924, Hubble basically published in, November of 1924, he published this statement that if you look at variable stars in these odd spirally things that we see out there, such as the Andromeda spiral and the M33 spiral, the Triangulum spiral, are they in our galaxy or are they more distant systems? By looking at variable stars, he said we now have the striking confirmation that these so-called spiral nebulae are distant stellar systems. They are not weird-looking systems inside the Milky Way galaxy. They are galaxies in their own right at distances of not thousands of light years, but millions of light years. So in other words, that put the nail in the coffin of the great debate of the 1920s, trying to work out, is the Milky Way all there is to the universe, or is there something outside our galaxy? And the answer is yes, there is something outside our galaxy, 1 trillion other galaxies. So the universe suddenly got an awful lot bigger overnight. So Hess showed us that most cosmic rays don't come from the sun, they come from something more distant. But how distant are these cosmic rays? Are they coming from the Milky Way or somewhere else? So Hubble, back in the 1920s, basically produced a paradigm shift and told us that the universe was a lot bigger than we had first thought. And so we can rephrase the question, are the sources of cosmic rays galactic, i.e. inside the Milky Way, or are they extragalactic coming from other galaxies? It is thought that supernova might be a possible source. This video consistently repeats. I can't get it to stop repeating. So supernova don't go bang and then decide to go bang a second time and then a third time and then a fourth time. It's just a looping video. But it is thought that the shock wave that comes out of a supernova, and possibly a shock wave that comes out of a supermassive black hole that's producing jets of particles, maybe those shock waves are responsible for accelerating particles. I'm not sure people really understand the mechanism, but they're saying that supernova and supermassive black holes are really energetic phenomena, so maybe they've got enough energy to somehow accelerate the particles to very high energies. It's thought that maybe the shock wave will accelerate a particle over and over and over and over again and raise it to higher and higher and higher energies. But I think it's fair to say that we don't really understand how. But we know that supermassive black holes do produce enormous amounts of energy. For instance, this one, Hercules A, is this galaxy right in the middle there. Next door is a small spiral galaxy. Maybe that's similar to the Milky Way. So just to get an idea of scale, perhaps that's about the size of the Milky Way galaxy. The Hercules A is much bigger than the Milky Way, but the supermassive black hole at its core, like all black holes, is tiny. It's probably no bigger than our solar system. Almost certainly it's no bigger than our solar system. So right in the center of this galaxy is a supermassive black hole, and it's generating so much energy, it's producing jets that are coming out and are not simply slamming into the interstellar medium within that galaxy. So much energy is coming out, it's slamming into the intergalactic medium. It comes out of the galaxy, and millions of light years later, it's still got enough energy to produce shock waves as it hits the intergalactic medium. So an enormous amount of energy must be pouring out of that supermassive black hole right at its core. And perhaps that is the engine that by some means or another is driving these cosmic rays to ever higher energies. So can't we work that out? Can't we just figure out which way these showers are pointing and trace them back to their source? Shouldn't that be easy? I mean, that's all we need to do, is to find a few showers and say, well, they came from, oh, that object there apparently is the source of the cosmic rays. Much like when light comes from a distant galaxy, we say, okay, that's the galaxy that produced the light. Should be simple. Unfortunately not, because we're dealing with charged particles, positively or negatively charged particles, and they will bend in magnetic field. Generate a magnetic field, a charged particle will bend to the left or bend to the right. That's assuming you have a nice uniform magnetic field. But unfortunately, magnetic fields are everywhere and can be quite complicated. Even the relatively simple field of the Earth will deflect charged particles. So charged particles coming from the sun, for instance, will end up spiraling around the Earth's magnetic fields, which is why we tend to get aurora around the north and the south poles. Magnetic fields appear to be everywhere. We can easily work out magnetic fields around a bar magnet, but how do we work out what magnetic fields exist in the Milky Way or between galaxies? That's a much more difficult problem. So we don't have a whole load of iron filings out there that we can rely on. We do have dust, though, so you can actually see dust out there in the Milky Way, and dust, in a sense, behaves like an iron filing and allows you to sort of map out what the magnetic field of the galaxy might look like. But it turns out to be really complicated, and simulations say, well, the magnetic field lines of the galaxy are going to be really complicated, and if we're trying to work out where a particle has come from, if the particle is deflected by these magnetic field lines, and we don't really know where these magnetic field lines are, it's going to scramble any knowledge we thought we had of where the particles are coming from. And we assume there must be magnetic field lines in between galaxies as well. But again, we have no easy way of measuring those. So if they are coming from a great distance, it's probable that our knowledge of where they're coming from is getting scrambled. We might think they're coming from over there, but they've been deflected. So they're actually coming from over there. And that really doesn't help us try and pin down the source. The one possibility is, we know from our physics lessons, the more energetic a particle is, the less it's deflected by a magnetic field. If you've got a very energetic particle, it needs a really big magnetic field to get it to move. So maybe really, really, really high energy cosmic rays won't be deflected much. So if we look at one of those, we'll get an idea of where they've come from. So how many particles are we expecting as a function of energy? I'll deal with the energy units in just a moment. The flux units are, well, they're silly. Let's get rid of them. The flux units are how many particles arrive as a function of energy. We get lots of low energy particles. We don't get many high energy particles. We think the lowest energy stuff is probably coming from the sun. The middling stuff is probably coming from the Milky Way. And it is thought that the only way you can get the really high energy stuff is by looking at more distant galaxies. What is the energy scale down here? Physicists use this rather odd unit of EV. What does that mean? Well, all we need to know really is that on the left-hand side there, an EV means the amount of energy in visible light. So the photons that are currently hitting my hand, they have an energy of 1 EV. We don't have to worry about what the unit is. We'll just use that as the unit, as it were. If we go up to much higher energies, in other words, if we go to something 1,000 times more energetic, we get to X-rays, and we're familiar with X-rays being more penetrating than visible light. And if we go up another factor of 1,000 to 1,000,000 EV, we get to the sort of energies that we saw coming out of radioactive particles. Alpha, beta, gamma particles coming out of a rock might have energies of millions of EV. But that's still tiny compared to the sort of energies we're talking about for cosmic rays. They will be all the way up to 1 billion, 1 trillion, 1 quadrillion. I don't even know how many zillions this is, but they are really, really high energies. Just for context, the Large Hadron Collider, a particle accelerator here on Earth, has an energy indicated by that left-hand arrow. If they ever get the funding, they're going to build another accelerator called the Future Circular Collider, and that will have an energy about there. So you can see that we're still talking about millions of times higher than the possible energies that we can produce here on Earth. So that's what this scale down here means. So how many particles can we expect as a function of energy? Well, the low energy stuff, we might get one of these particles hitting every square meter of the Earth's atmosphere every second, and then remember producing a shower of secondaries. If we go to higher energies, we get rather less of them, 1 per square meter per year, very much less common. If we go to the very highest energies, 1 per square kilometer per year. This is why we need detectors that are many, many thousands of square kilometers so that we've got a chance of catching these very high energy events. And we have caught 1 or 2 over the years. So back in 2023, the telescope array, which is an array in Utah, USA, it was reported in Astronomy Picture of the Day a few months ago, December 2023, that they'd seen a very energetic particle. They actually saw it in 2021. It's taken them a while to analyze the data. Something humongously energetic hit the top of our atmosphere and produced a large shower. Only a little bit of that shower clipped the array, but still they could work out how energetic this particular particle was. Turns out it was the second most energetic particle ever seen hitting the Earth. It was called the Amaterasu event. Amaterasu is a Japanese goddess. It translates as shining from heaven, a very nice way of thinking about this. And you would hope that this is energetic enough that you might say, if it really was that energetic, maybe it's not affected by magnetic fields, so maybe if we work out which way that is pointing, we'll stand a chance of working out where it came from. Bear in mind that the Amaterasu event should not be confused with the tiramisu event, which is what they ate at the celebration party when they realized they'd caught this very energetic particle. So if it really is this energetic and ultra-high energy cosmic rays, let's hope that the magnetic fields that are out there are not strong enough to deflect it, in which case we can work out which way it's pointing. So they did that. They calculated, based on what they were receiving on the array, which way this particle had come in, and they basically traced it back to a patch on the sky. And they found that the direction points to, pause for dramatic effect, nothing. No supernova, no supermassive black hole could be found in the region that they were looking at. There was no obvious candidate for what was producing this enormously energetic particle. So does that mean that the source wasn't a supernova or wasn't a supermassive black hole? Or does it mean magnetic fields out there are stronger than we figure and it's been deflected and actually came from somewhere else? We don't know. We need more data. We need more observations to tell us where are these really energetic particles actually coming from. Let me finish by giving you an idea of just how energetic these things are. How close to the speed of light was this second most energetic? No, let's not take that. Let's take the highest energy particle ever seen, not the Amaterasu event. Let's take the most energetic particle ever seen. It was called the oh my God particle because when they saw it, the scientists could genuinely not believe that any individual particle could possibly possess that much energy. They had to double check and triple check and quadruple check their calculations to be sure that they really did have a particle that energetic, right at the extreme right-hand end of that chart I showed you. How fast was it traveling? Well, expressed as a percentage of the speed of light, remember, a more energetic a particle is, the closer and closer and closer it gets to the speed of light in a vacuum. They reckoned as a percentage of the speed of light, this particle was traveling at 99.99999, not done yet, 999, still not done yet, 999, we're getting there, 995% of the speed of light. That is a ridiculous speed for any object to be traveling. And it's really still a mystery as to how you can accelerate a particle to that sort of speed. That, even if you count the nines, it's very difficult to get your head around what that actually means. So let me try just giving you a visualization of just how fast this particle is. Let's imagine you had a race between a particle of light, a photon of light, a beam of light if you prefer, and a cosmic ray. Let's give them a racetrack which is 100,000 light years long. So it's roughly speaking a racetrack roughly the size of the galaxy. And let's assume they are hypothetically doing this race in a perfect vacuum so we don't have to worry about the speed of light not being the speed of light. So how fast will they go? They'll start at the same point, they'll start at exactly the same instant, and the light and the cosmic ray will have a race. The light will win because nothing can travel faster than light in a vacuum. So light will win, but the question is, when the light travels across the finish line 100,000 years after they start, how much ground would the cosmic ray have lost? They start at the same point. When the light ray crosses the finish line, how far behind it is the cosmic ray after a race of 100,000 light years? The answer is 5 millimeters. It is 5 millimeters behind it after a race of 100,000 light years. If you had a stopwatch, you could say, after the light has traveled and crossed the finish line, start the stopwatch, how long before the cosmic ray crosses the finish line? The answer is less than a nanosecond later. Much less than a nanosecond later, after a race lasting 100,000 years. This is still one of the biggest mysteries around as to how anything can go that fast. So let me summarize. Cosmic ray particles are accelerated somewhere, somehow. We don't know where, we don't know how. Maybe it's supernova or supermassive black holes, the jets of supermassive black holes. They are probably sources, but we haven't been able to pin that down. They are deflected by magnetic fields because they're charged particles, and we assume that the low energy ones get completely scrambled because of the magnetic fields. Maybe the higher energy ones travel in straighter lines. That might be the way we pin down their sources. Some of these particles make it past Earth's protective magnetic field. The Earth's magnetic field protects us from a lot of particles from the sun, but it doesn't protect us from all of these cosmic rays that we're seeing. When a particle hits the Earth's atmosphere, it produces an air shower of secondary particles, and some of those secondary particles make it to sea level. There will be muons, electrons, protons, and ultimately they make clicks in Geiger counters, and they make tracks in cloud chambers. I put the Geiger counter back on to remind us that we are listening to cosmic rays. We've seen the tracks before. I'll bring them back on momentarily. So cosmic sources are producing these. Just listen to the clicks. Every click signals the arrival of a cosmic ray particle which may have started its journey in a supernova or possibly in the jets of a supermassive black hole. So every click you hear, you're listening to the cosmos. Thank you for listening.